today we'll have an introduction into thermodynamics, which is the study of energy transfer that involves heat and work, and the resulting changes in macroscopic properties of a gas. So basically we're going to look at ideal gases and the macroscopic properties, pressure, volume and temperature, and how heat and work also influence the internal energy of a thermodynamic system. And basically heat is defined as the thermal energy that's transferred between bodies. Now the equation of state that relates the macroscopic properties of a gas, and specifically an ideal gas, is the ideal gas law, which states that pressure multiplied by volume is equal to the number of moles multiplied by the universal gas constant multiplied by the temperature. And the universal gas constant, which is the same across all different ideal gases, is equal to 8.314 joules per mole Kelvin. And basically what the temperature is a measure of the internal thermal energy of the ideal gas due to the motion and interaction between the molecules. Now certain assumptions are made to consider a gas as ideal, and one of those is that the particles of gas are in constant random motion. So they keep moving around at different velocities randomly. So in this box it's going to be like a three-dimensional motion. So the velocity can be in the vertical, horizontal and z direction. And the second assumption is that the gas particles have negligible volume compared to the volume of the gas, so versus the volume of the gas. And the third assumption is that there's no intermolecular forces between the gas molecules. So although there's negligible intermolecular forces, so for example if we had neon gas, you'd have London dispersion forces between the gas molecules. So because they're quite weak, we tend to ignore them. But if you look at H2O gas as another example, well in this case you'd have your dipole-dipole interactions between the hydrogens and oxygens, and therefore the intermolecular forces are quite significant, and this cannot be treated as an ideal gas. And the other main assumption is that the particles only interact through elastic collisions, so between the particles and the container, the collisions are elastic, meaning that energy and momentum is conserved. Now one thing to note about pressure, so if we look at the interaction between the particles and one of the walls of this container, well pressure is defined as the force on area. So therefore the interaction between these particles, where there's many of them, so therefore the interaction between these particles and the wall at a given time are going to exert a force on that wall. And the force on the area gives you the pressure due to the forces imparted by these particles on the wall container. And also pressure can also occur at any point in the gas. So if you take an element, you're going to have the gas exert a pressure on this element. Now another way we can represent this ideal gas law is using Boltzmann's constant. So if we look at the number of moles, we can write this as the number of gas particles on Avogadro's number. So note that the number of gas particles is just going to be particles, and Avogadro's number in this context, where we're looking at gas particles, is going to have units of particles per mole. And therefore the particles cancel and you get moles in the numerator. So that's the relationship between the number of moles of gas and the particles of gas using Avogadro's number. And Avogadro's number is 6.022 by 10 to the 23 particles per mole in this case. So therefore we can make our substitution in the ideal gas law for the number of moles. So we get pressure by volume is equal to the number of particles of gas multiplied by the universal gas constant over Avogadro's number, and that's multiplied by temperature. And this here is another fundamental constant of nature known as Boltzmann's constant. So another form of the ideal gas law is basically written as PV is equal to the number of particles of gas multiplied by Boltzmann's constant multiplied by the temperature in kelvins. And Boltzmann's constant is equal to 1.381 by 10 to the negative 23, and the units are joules per Kelvin. So that's consistent with the universal gas constant on Avogadro's number. And I'll see you in the next video.